Welcome. In this lecture, which has multiple sessions, we'll explore some of the intuitions behind a Lagrange multiplier. The main concepts that we'll go through is that for a constrained optimization problem, a minimizer of that constrained problem is on a level curve of an objective function. That minimizer is also on a level curve of a property function. And indeed, it's at the intersection of these level curves. So what we'll find is in our examples, these level curves have parallel gradients at that intersection. And we're curious about what happens in general. As our first problem, let's explore one that we've looked at in a previous lecture, which is what's the minimum length vector that is on a 2D line. Let's work through some mathematics. Let's recall this problem. The problem that we explored in a previous lecture was we want to find the stationary point that is the minimizer over all points in a 2D vector space of a first function that has a vector argument. And the way that we wrote this was this function that has a vector argument was the squared norm, and there are many ways to write the squared norm. Here I'll write it as the transpose of the argument times the argument, and our property function of any vector was, we would compute that as we would the one form of minus 1, 1 times the argument plus 3. And in this constrained problem, what we'll do is we'll require that the property at this optimal point has to equal 0. So this is a convex constrained optimization problem. Let's draw this out. We'll draw it by hand first. And it's a good idea if you draw this out along with me. Here we'll put the horizontal is our first component of the vector. The vertical is the second component. Here's the origin. And what this line will look like is it will look something like this. I won't put the exact coordinates on, but it'll look something like this. And we can see that if we were to pick a level for the function, and the level was 0, that would just be the origin, and the origin isn't on this line. And then if we increase that a bit and we picked another level, this level curve still wouldn't have any points that are on that line. And if we increased it a little more, there would still be none. And if we increased it too much, what would happen is we'd have 2 points that are on the level curve and also satisfy the constraint function. That is, these are on a level curve of the function and they're on the constraint line. So now we can imagine that there is some, if we can think of how many geometrical solutions are to the problem of intersecting a circle of a given radius and a line. And the answer would be, well, if we pick this radius, there are 0 points that are on the intersection. If we pick this radius, there are 2 points. And we could reason out geometrically that there is a radius such that if we pick that radius just right, then there's exactly 1 point that is on that level curve and on our constraint line. So let's go through a computer-generated example that's going to be much better than my hand-drawn example. Now, the way that we formulated this was our objective function was the squared norm of a vector, and we had a linear equality constraint. So if we increase the level until the level curve touches that constraint line, what we see is that the optimal point for this first function is at these coordinates. And this is what it will look like. Now this is the computer-generated version of what I just drew. And we can see now that here we have the levels of the quadratic function, and here we have the constraint line, and there will be some level at which those exactly touch. If we compute the gradient, that'll be a one form. If we transpose that gradient, it will be a vector. And that vector, as we've seen so many times in our contour plots, will be perpendicular to the contour. And so what we would find is that this cyan curve, this cyan arrow, is the transpose gradient of that circle, and the red arrow is the transpose gradient of the constraint line. And we can see that these are parallel. They happen to be directed oppositely. And the multiplier between the two of these is the value 3.